Hello and welcome to this meeting. We're going to be talking about quantum applications in blockchain. So let's get to it. So a little overview, we're going to talk about blockchain very quickly, kind of explain what it is, an application of it, obviously Bitcoin and Ethereum. And then we're going to talk about the security of it and what happens after quantum becomes broadly available. And then we're going to talk about the field of cryptography. So how does quantum affect that? And then some limitations and some practicality, how much of it has been done already and all that kinds of stuff. So blockchain, what is it? In the most basic form, blockchain is a way to store documents such that changing these documents and tampering with them would be really hard. So we basically want to mathematically somehow do this. And how it works is basically on top of hash functions. So what is a hash function? It's basically a string that basically a function that maps an input string to an output string. And it does it very with a high entropy. And what that means is that basically if you change the input string even a little bit, the output string will change a lot. And this is already getting used in Git, for example. They're using SHA-1 to compare if a file has changed instead of comparing them line by line. So it's very fast to compute. And here's a structure of a block in blockchain. So you basically have all the data that you want to store. And then you have the previous block's hash. And then you have some nonce value this is basically the value that gets generated by your miner. So the trick here is to take all of this and compute its hash. And then if that hash has like a whole bunch of leading zeros, that means that you have a valid block. So to find some nonce value that you can generate such a hash value is really hard. It's basically the only way that you can find that nonce value is to brute force it. So that's what a miner does. And in this case, for example, we're requiring that there's 12 zeros here because this is hex. And this is called proof of work. And as a result, your blocks become very secure because if you change some data here, that'll invalidate the hash for this block, which results to the invalidation of this hash of this block, and so on and so forth. So it makes it very, very secure. Here comes the question of quantum supremacy. So what if we're basically using the fact that these problems are very mathematically hard to solve to make our system secure? So what happens if there's some quantum computer that can solve these problems in a much, much faster way? Then the security will break. So that's basically what we're going to be. So the question basically becomes, are there quantum algorithms that can break our hardness assumptions? And the answer is yes. A modified version of Shor's algorithm, for example, can break the ECDSA key pair generation, which gets used both in Bitcoin and Ethereum. So in the next couple of slides, we're going to be talking about that. And that's it for me.
So to understand why ECDSA is difficult, we first look at the EC, or the elliptic curve. And we can see an example of one over here on the left, defined over a continuous space. We can take that same curve and define it over a discrete space, specifically one that's modulo 11, or modulo a prime number, and in this case, 11. And we can also take all those coordinates and put them into this set over here. And before I go on, there's an operation, a point multiplication, which is kind of like a multiplication, but it's acting on both the x and y coordinates, so it's a bit different. And the reason we care is because we can actually look at this set. We take any point P in that set, and we can represent every other point in that set as a point multiple of that point, which is really cool. So like this is, say this is P, then this would be 2P, 3P, 4P, and so on. And it kind of forms this nice cycle. So given an elliptic curve, given a prime number to modulo over, given the number of solutions in that discrete set, and then taking two random or 2 points in the set, the question is, find M such that Q is the mth point multiple of P. And the cool thing about point multiplication is we can actually write it as a logarithm. So M is actually log base P of Q, hence the discrete logarithm problem. So Pollard's algorithm is the current best solution for this, and it is exponential. So that's why this problem is so difficult and useful for cryptography. Now, before we go on to the quantum solution, I'm going to talk quickly about the quantum Fourier transform. And it makes use of these 2 quantum gates or quantum operators. The first one is the Hadamard gate. The second one is the rotation gate. Here in this image in the center, we see the quantum circuit implementation. So each line is a qubit, and we can see that each qubit goes through these set of operators, a set of gates. And we end up with the Fourier transform looking like this equation here at the bottom. Each set of brackets is basically one qubit. And so on to Shor's algorithm, how we're going to solve the discrete logarithm problem. Let's first start off with two registers. So a register is just an array of qubits, so two arrays of qubits, and we initialize them to ket state 0. Then we're going to take the quantum Fourier of this state to put it in the superposition of numbers a and b mod p minus 1, because this is a more useful form for us. Then we apply a function based on the first two states, and we apply it to now, or based on the first two registers, and we apply it to a third register now. So in this case, we're using p to the a, q to the minus b. And this is actually representative of our point multiplication relationship. And then we apply another quantum Fourier transform. And at this point, now we're going to calculate the probability of this state here of being in the state c d p to the k mod p. And if we look at it, or if we think about it, d plus mc, if d plus mc is not equivalent to 0 mod p minus 1, then the probability ends up being 0. If it is equal to 0 mod p minus 1, then the probability ends up being 1 over p minus 1 squared. So we only care about pairs of c and d such that mc plus d is equal to 0 mod p minus 1. And so we can finally calculate our goal of m by computing m equals negative c to the negative 1 times d mod p minus 1. And this operation, now that we've gotten this far, we can actually do this in polynomial time, which is a huge step up from exponential time, which is very, very cool.
So post-quantum cryptography, there are a number of different cryptographic algorithms that don't degrade in how complex they are to solve when quantum computing is introduced. So obviously quantum computers are faster, but they don't degrade in complexity from, say, exponential to polynomial time, as in the case of ECE. So the one we're going to focus on today, though they're all quite different, is hash-based cryptography. Hash-based cryptography takes advantage of the fact that when you have an input and you create a hash of that, that is a very easy process, but to go back from the hash to the input is very difficult. You basically have to take a brute force approach, which is not made significantly easier using quantum computing. So how the hash function is used is it's used in a one-time signature scheme. Lamport-Diffie and Winternitz are the two basic ones. And when you have the hash, it is a fixed number of bits every single time. So you create two random numbers for each of those bits, and that's going to be your private key. The public key is the hashes of those numbers. The signature is going to be only half of the private key based on an algorithm that is used, and that algorithm is based on the hash of the message. So what happens is the recipient can run the same algorithm and hash the message and check which of the public key hashes are supposed to be used and make sure those match the hashes of the half of the private key that's in the signature. So obviously this can only be used once because you do have half of the private key in the signature, so more times is going to make the private key less and less secure. So how we get around that is by using Merkle trees. Merkle tree is basically a tree of hashes where each node is the child of its hash nodes. So in the Merkle tree signature scheme, each of the leaves of the tree are going to be a public-private key pair using either Lamport-Diffie or Winternitz or a derivative. And once you build all of the hashes up to the top, the root hash, that's going to be your public key. Signature verification is done as follows. So let's say for a Merkle tree signing scheme, you can only sign n times, where n is the number of leaves. So in this case, you can sign 8 times, each time with a different private key. So in this case, we're going to use the third one. So the signature is going to be A0 plus all of the hashes required to get back up to the root node. So A0, auth0, auth1, auth2. And that's going to be able to get you to A3, which should match the public key, the global public key. If it does, you have a good message. Otherwise, you have a fraudulent message. And this is not easily broken with quantum computing because there's clearly a lot of hashing algorithms that are going to need to be broken in order to do this, which is not something quantum computing is good at yet. Some modifications. XMSS is pretty cool. Is what is used in quantum resistant cryptocurrencies today. It is forward secure, which means cracking one private key doesn't crack any of the previous messages that have been sent, and it has minimal security assumptions. GMSS is just kind of cool in that it allows an unlimited number of documents to be signed with the same public key. So the quantum resistant ledger. This is the one that's in use today. It is a new cryptocurrency. It is supposed to be future-proof and withstand attacks from quantum computers. It does use XMSS for signing and verification, which we've already proven is resistant to quantum computing attacks. And how it gets around the XMSS only allowing a limited amount of signings, which I think is kind of cool, is that it has a proof of stake algorithm where once you get to the end of one tree, you sign all of the relevant stakeholders, send secure messages back and forth in order to decide on the seed of the new XMSS tree. So those trees are chained one after the other, and you can sign infinite number of messages in this way. So this is the cryptocurrency in practice today that is future-proof against quantum computing.
So far we've seen how quantum computing can be used to easily break the blockchain implementation, as well as some of the newer cryptographic schemes that could potentially coexist with quantum computing. Taking a step back and looking at the general practicality of quantum computing, it will mostly lie within cryptography, solving complex problems, modeling, as well as faster data processing. In particular, relating to our presentation topic, it will be on cryptography as well as solving a search problem. So to break ECE, we are basically searching for the private key in the signature agreement. In terms of cryptography, ECC and RSA can both be easily broken by quantum computing, and thus it's important as we become more and more reliant on digital communications to devise a cryptography scheme, perhaps leveraging quantum cryptography to securely encrypt our data such that we won't lose confidentiality when we are communicating with each other. So with that being said, there are some limitations related to quantum computing. The first of all being errors in physical qubits. So the qubits themselves are not error resistant. So one way that researchers have been trying to solve this problem would be to group a bunch of physical qubits into one virtually error-free logic qubit, which isn't really practical because we need a mass amount of physical qubits to build one logical qubit, which the ratio is usually in thousands to 1, which won't get practical as you need more qubits. The second problem being quantum decoherence, which is basically a loss of information to the environment, which would reduce these qubits to their classical behavior, so either 0 or 1, but losing their superposition behavior. And we are expected to leverage and rely on the undisturbed states for quantum computing, which brings us to the third point of temperature requirements. So typically we've known that quantum computers would require a lower temperature to keep them in a stable state, which is another limitation. So lastly, some of the future research in the area of quantum computing could be fault-tolerant qubits, as well as quantum algorithms, with related to the specific of applying quantum computing to blockchain. It could be leveraging post-quantum cryptography, as well as newer blockchain algorithms, such that the ledgers would still be quantum resistant, and to build these newer blockchain implementations. And thank you for listening to our presentation. And the following 2 slides will be our references.